Okay, so I already have videos on finding limits from graphs and tables, which is like the first most of the homework. The last one of the homework is using an equation. So that's what this lesson is all about.
Okay.
So first, just all of these videos, I like to just get into the background. What is a limit? We've talked about these before when you've learned end behavior of a polynomial and asymptotes of a rational function. Those are technically limits. And it's the asymptotes of a rational function that is really what you're looking at with number 5. Depending on where you've taken college algebra, you see notation that's similar to limit notation, where you have an X and then an arrow and then whatever it's approaching.
Mhm.
Some college algebra books don't use that notation. It kind of depends on the textbook. But you're basically saying, as I get to some specific X value, where is my Y? And we've got just the general limit where you're looking at what's happening to Y when on both sides as you're
Mhm.
coming from the negatives through the positives. And then we have one-sided limits where you're looking at one side and you don't care about the other side.
Okay.
So most limits you're looking at what both sides are happening. And so in order to do that, you have to have them, they need to match for both sides. Otherwise, you've got a one-sided limit. And there are some limits where if you're going to limits to infinity, those are only one-sided because you can only get to infinity from one side. So those we usually don't use the plus or minus notation that I have here because positive infinity, there's only one way to get there. Negative infinity, there's only one way to get there. Otherwise, in numbers, you have 3 choices and you have to kind of pay attention to whether it's got a plus, a minus, or if it's just by itself.
Okay.
So because we've got equations, you can find the limit graphically or with a table, but you're intended when you're just given an equation to do it algebraically. Now we can do it with calculus, but you guys haven't learned calculus. So, that's something you'll learn in calculus is some more techniques for doing it. But right now, all you know is algebra. and so those are the methods that we're going to use. So if your function is continuous, meaning that there's not a gap, there's no asymptotes, no vertical asymptotes, there's no jumps in your equation, or like it's not a piecewise equation, which means any polynomial, linear, radicals, exponentials, those are all continuous functions. You can do direct substitution. You just plug in the number that you're interested in, and that's going to be your limit. Rational functions, which is what we have on the homework, that's a little different.
Okay.
Sometimes you can plug in the number, but if that number is not in the domain, say you end up dividing by 0, that's not going to work. So then you have 2 other options. You can factor and simplify and then plug in the number, or you have to do this technique called rationalizing. And that's specific to if we have rational functions that also have square roots, because we usually talk about rationalizing something when there's square roots involved. So we're going to kind of do examples of all of these so you can see how they work. So direct substitution means you're just plugging that number into your function. So you can do this for polynomials as long as it's not like a rational function, you can basically do this. Now, the important thing is how you write your notation here. So that limit, I see a lot of people writing the limit when they don't need it, or not writing the limit when they do need it. So when you are taking the limit, basically doing the action, meaning plugging stuff in, that's when the limit disappears. So when you're doing direct substitution, you're plugging that value you're interested in, which for this first one is -3. You're plugging that in for X. And when you do that, then you don't need that limit notation anymore. So when you plug stuff in, the limit disappears. because now you are doing the action of taking the limit. And I don't know what -3 to the 4th is. So I'm going to do that on my calculator. 81. Okay. So we have the limit of x goes to -3 of x to the 4th. So you're just plugging -3 in. So you get -3 to the 4th, which is 81. So your limit is 81.
I got -81. Maybe it's my calculator. Maybe
You have to put parentheses around the -3.
Okay.
So if you don't, what you're telling the calculator is to do the 3 to the 4th and then have a negative in front. But we're doing -3 to the 4th.
It's important.
Yes. Yeah. I mean,
It's the
it may
difference between
seem
a right answer and a wrong answer.
exactly these little things, these little parentheses, they make a big difference. So it seems kind of silly to do the limit in a problem like this when you're just literally plugging in the number, and it kind of is, but it's getting you used to the notation. Normally you don't bother doing a limit for something like this because you would just say, what's the value when I plug in this value for x?
Okay.
So the next one I also have, we're doing the limit as x goes to -3. And this is a linear equation for x minus 1. So it's continuous, so we can plug -3 into our 4x minus 1. We're plugging in for x. And when you do that, the limit disappears. So you just have 4 times -3 minus 1, which is -12 minus 1, and we get -13. So nice and easy as long it's continuous. And basically, most functions are continuous. So you don't, if you have something that doesn't look like a fraction, you're basically okay at doing this. And you don't have to worry. So it's when we hit the rational ones that we can't do this, and we have to look at different methods. And so we're going to do these two by factoring and simplifying. So the first one on top, I have the limit as x goes to 0 of x squared plus 3x over x. So I can't just plug in 0 for x because then I'm going to be dividing by 0 in the denominator, and we can't do that. So that's why we have to do another method. And if it's something that you can factor, that's going to be the method that you're going to want to try. Now, not everything can factor, but if it does, it's going to make your life a lot easier. So this is sort of, I'm kind of going in the order of the techniques you want to try.
Okay.
First see if you can plug in the number, and if you can't, move on to the next one to try.
Okay.
So how this works is we are going to factor our numerator, and then we're going to cancel things out and then take the limit. So I can factor an x out. And when you're doing this, this is where you still have to write your limit stuff because we haven't actually taken the limit yet. So you're doing all this algebra, but you still have to write that notation because you haven't done the limit. You're just rewriting your actual function. So this is where people usually stop writing the limit, but they haven't actually done the limit yet. So technically that would be incorrect.
Okay.
So when I factor out that x, you can see that I have an x on top and x on the bottom, and those can cancel out. And so
you only have a 3.
Yes. And that's nice because now we don't have a fraction anymore. And now we have something that we can plug. We can do the direct substitution in because now I can just plug in 0 for x.
Got it.
So when I do that, then the limit disappears and we get the answer of 3. So same sort of idea with the next one. We've got the limit as x goes to -1 of x squared minus 1 over x plus 1. So, I mean, you can factor the top or the bottom or both. In this case, both of these examples, we want to factor the top. Now, if I plug in -1 to x, again, I'm going to get 0 in the denominator because I have x plus 1 and those would cancel. So our x squared plus 1 factors to x plus 1 times x minus 1. And then this is x over x plus 1. And so you can see, again, we get to cancel things out. And so then that brings us to something that is continuous. We're going to have the limit as x goes to -1 of x minus 1. Now I can plug in for x. So my limit notation disappears and I just have -1 minus 1. And so we get -2 for the limit. Now, of course, not everything factors like that, and you can't use this technique. The one reason why I hate limits is because these are like, you try this, if it doesn't work, then you try this, if that doesn't work, and you have these like different things to try.
So this is what I've got. So first we're going to do substitution, then we're going to try factoring.
Mm-hmm.
What's the third one?
Third one is to try to rationalize. And so this is where you specifically have a square root in there. Obviously, we can't factor or simplify anything here. Now, not the rationalizing doesn't always work either. This particular one is designed so that it will work, to kind of show you the technique, but it doesn't always work. So we can't just plug in 4. We got the limit as x goes to 4 because that'll be 4 minus 4. Again, I'm dividing by 0. That's the big thing with these rational ones, is that you tend to divide by 0 and then you've got a problem. So what we do now, normally when we were talking about rationalizing, we always talk about rationalizing the denominator, because you'll have like a square root in the denominator. In this case, we've got a square root in the numerator, and you might think, well, that's not a problem. I can plug 4 into there. I'm totally okay. But just to kind of demonstrate what happens here, if I try direct substitution and I plug in 4 for x, I'm just going to do this specifically in a different color so you can just see. We end up with the square root of 9 minus 3 over 0 and 3 minus 3 over 0. You end up with 0 over 0. And this has a special name. This is called indeterminate form.
Mm-hmm.
And this is because 0 on top, we should get an answer of 0. 0 in the denominator, we should get an answer at undefined. So if you get 0 over 0, it's like, well, which one of those? So it's called indeterminate. Like, we don't know. we don't have a name for this.
Okay.
So that's where, even though it looks like the top is okay, it's not really okay, because we ended up with this. We don't know what's going on here. So what we do, and I'm going to again rewrite this. I know it takes some time. So we look at what is on the numerator, and we're going to multiply by the conjugate, which is basically just changing the sign between the two terms. And then I have to also do that in the denominator. And so now we're going to end up with a square root in the denominator, and you're going to think, well, that's not going to be a good thing, but it actually will end up being okay.
Okay.
Don't worry. Don't worry. Because once the thing about calculus, and you'll learn this when you take it, is that we have these rules: no square roots in the denominator, no negative exponents. We always want to rewrite it. When you get to calculus, you find that a lot of the things you need to do are easier if you ignore those rules. So once we get to calculus, we're okay with square roots in the denominator. We're okay with negative exponents because it makes our life easier. So all of these rules that you learned in college algebra kind of get thrown out the window when we hit calculus.
Okay.
I'm not sure why that is.
It
It's
sounds like you're making up the rules as you're going along. So.
you know, it kind of is. If you look at the history of algebra, it doesn't really get standardized until the 1800s. So
Okay.
all this math that was going on, the math for calculus was invented in like the 1700s or 1600s. The rest of the math was before then, like it wasn't really standardized. We didn't even have standard symbols. So yeah, it was kind of made up until,
Okay.
you know, until they decided, okay, we should probably get together and have like the same symbols.
Yes. All right.
But you're kind of finding as we get into calculus that you're like, yeah, they kind of did what they needed to do.
Yet they still came up with the right answers. Go figure.
It's pretty amazing.
-4.
So we've got a FOIL on the top. And so the square root of x plus 5 times the square root of x plus 5, those square roots cancel. So we just end up with x plus 5. Then your inside and your outside when you try to FOIL are going to cancel, because you're going to get a -3 times the square root of x plus 5 and then a +3 times the square root of x plus 5. So those are going to cancel. That's why we're doing this conjugate. And then we're going to have -3 times 3. So that's going to be -9. And I don't try to multiply in the bottom. Just leave it as is. So when we simplify on top, we're going to have the 5 minus 9. That's x minus 4. And oh, we've got an x minus 4 in the denominator, so that's going to cancel out. So that's a little trick here, is that it cancels out one of the things that was causing us problems. Because that x minus 4, when you plugged in your value for x, we got 0. So now that's gone. Oh, and I just did the cardinal sin that I was saying, don't do that. Now I got to squeeze it in. I do this too. I got to make sure that I have my limit at each of these.
Yep, because you didn't actually solve it.
Yep. It's like you do all this algebra and then you're like, shoot, I forgot to write the limit there.
Sorry, I did too.
Yeah, it happens. It happens. That's why I point it out and be like, even I do this.
So that means you have nothing in the numerator.
Right. We just have 1. Basically, when it cancels out, you just kind of put a 1 there. So now I can plug in 4. Because now I've canceled out one of the problematic parts. So now I can lose my limit. So I plug in 4 for x. So we get 1 over the square root of 9 plus 3. Which is 1 over 3 plus 3. And we get 1 over 6 as our final answer. So it's got a lot of algebra. Like students in college algebra ask me, why do I need to know how to do these things with radicals and all this? And I'm like, calculus.
Right.
Because you will need to do a lot of algebra in calculus.
9, so that's 3 plus just say 1 with 1 over 6. Okay.
Mm-hmm. Yes. Now, of course, not every problem works out nice like this. You can try to rationalize, and sometimes things don't cancel, and then you can't use this technique.
So there's a fourth technique?
That would be using calculus.
Okay.
So at this point, if you're trying to do something like this and it doesn't work, then you have to resort to calculus, which you don't know yet. So
Okay.
these are all the things you do if you're looking for x going to a specific number.
Okay.
Now, number 5 is not asking for x going to a number, it's going for infinity. So this is different. Because of course it is. We're going to something
Of
else.
Yes, of course it is.
Yes. So
And I'll be honest with you, during the reading and following the notes and look, the infinity, I couldn't get next to it. So I'm hoping when you explain it, I'll grasp it.
hopefully it took me a while. When I was
To
getting
me,
my
infinity is just not a tangible number. It just, it means,
right.
it means something, but you can't quantify it.
Exactly. So you have
Right.
to think about it in terms of other numbers that are getting really big. I really struggled with this. So when I was getting my degree, you take all the calculus classes, and then there's a class called real analysis that you take after the calculus that actually teaches you the theory of calculus. It's like, why didn't we learn this first and then calculus? You know?
The reason why, yeah.
I don't know. So you finally learn why these things work. And that's where I was like, oh, that's why limits are the way they are. Like it suddenly made them
Right.
make sense. So when you're looking at things that go to infinity, you can look at the graph, like put it into Desmos, and then you basically have to scroll out a lot so that you can look at really, really big numbers for like X, either really small, like, negative a million or something like that, or really big, like positive a million. And that is basically knowing what the end behavior of the function is. So this is basically knowing the shapes of the functions and knowing what happens when you go to the endpoints. Like when you zoom out, what does the function look like?
Mhm.
So with polynomials, you learn about the end behavior, and you learn about whether it's, if it's an even, it's going to look something like this, or if it's odd, it's going to look something like this. So you learn about end behavior. And that's really what you're looking at when you're going to infinity. Is you zoom out enough, it's going to look like that.
I found that if you did x squared, that's how you got it on both sides.
Yes.
How it looped, right? Or
Yes.
the
Yeah.
first
So
one,
any
yeah.
even exponent kind of loops back up. And then the odds go they go opposite. For rational functions, again, you have end behavior because you have different shapes of rational functions. You have shapes that go like this. You've got shapes that kind of go like this. So you still have to kind of know the general shape, but there are also a couple tricks that you can use where you're going to do some division, and then you're going to use the knowledge of specific limits. And the one that you really need to know is 1 over x. So the limit of 1 over x in either direction goes to 0. And it makes sense if you think about it. So we can't obviously plug infinity in for x. That is not a thing. Now, in engineering textbooks, they'll do that, and it drives me batty because technically you can't do that because infinity is not a number. You can't just plug it in for x, but engineers do it all the time. But mathematicians do not do that. We can't just put in infinity for x, but you can think about what happens. So if you think about your knowledge of fractions, like 1 over x, and so you have a fraction like 1/2. If I have a bigger number in the denominator, like 1/10, that's a smaller number.
Mhm.
If I have something like 1 over 100, it gets smaller. The larger the number is in the denominator, the smaller the number gets.
Mhm.
And so as x is going towards infinity, your fraction is approaching 0. It won't actually equal 0, but that's where it's approaching. And so that's why the limit of 1 over x is 0. And it doesn't really matter which direction you're going towards. It's still going to approach 0, whether it's as you go to negative infinity or positive infinity. Because the number is still going to get...
It'll never get to 0.
Yeah, it never gets there. But for our purposes, if you're thinking about an infinity, which you can't reach anyway, we're going to call it 0.
Okay.
So that's the idea with rational functions. And this is just one limit that when you learn limits, you just have to know that 1 over x is 0, the limit as you go to infinity. It doesn't, if you go to a different number, it's totally something else. But if you're looking at infinity, it's going to 0. So I've got 2 examples here, and we're going to kind of look at these from 2 different directions. So we've got x squared over x squared plus 4. We're looking at what happens as x goes to infinity. So we can do this by looking at the end behavior of a rational function. So if you are thinking you've got some rational function, and I don't know off the top of my head what this particular graph looks like. So I'm going to just graph something. I don't think it's what this one's going to look like, but as you're going towards infinity, you're basically approaching your horizontal asymptote. So as x goes to infinity, your function y is going towards your horizontal asymptote. So all you need to do is find the horizontal asymptote for that rational function.
All right, so let's back up for a second.
Mhm.
So y is your horizontal asymptote. All right, so I get that. So the line is going to run horizontally, get closer and closer to 0.
Yes, on this particular graph. It may not always be 0.
Right. Okay.
Yeah, so this one is actually not going to be 0. I just drew one where it is 0 just so you can kind of see. So the way that we show our work for this, because like in college algebra, you just say, oh, horizontal asymptote is this, and you're just taught how to figure it out. But really what you're doing is a limit and you don't really know it. So the actual math that you're doing here, as x is going towards infinity, you've got these really large numbers that you're plugging into x squared. So in the denominator, adding 4 to some giant number that's getting squared really doesn't do anything because it's so small compared to this number that's squared. So when you're going towards infinity, basically any constant doesn't really matter. And it's the same thing as if you were just looking at x squared over x squared in this case. Because adding 4 to some giant number, still giant.
Mm-hmm.
So now we have x squared over x squared, which we can cancel out. That just gives us 1.
Yeah, that's what I was going to ask. Why couldn't you cancel them out? Okay.
Yes. Now, we haven't technically taken the limit yet. We're just canceling them.
Right.
So we're basically finding the limit of 1. And well, it doesn't matter what x is, you're going to get 1. So our answer is just
so you're just dropping the 4 entirely?
Yes.
It's not 1 over, you're just dropping the 4. And you're just
Yes,
saying
because
it doesn't matter.
When you square something, that 4 is so small compared to what this giant number you're squaring that you've still got a giant number. Okay. That's the way that I think about it.
That's a rule definitely just made up. Drop the 4 because this is why, and I understand why, but okay.
That's what limits are. Limits are when you're looking at limits at infinity, you're like giant number plus 4, still a giant number. So we're just going to call it giant number.
Okay.
That was actually how my professor described it to me in the real analysis class. So,
it makes sense, right?
Right, exactly. It makes sense. I'm like, that's coming from a PhD. So that's good enough for me.
Okay. Wow.
So that's one method, is just to say, well, if we're going towards infinity, we're looking for the horizontal asymptote. Here is the work that you show to get to this. There's an alternate method, and it's showed in one of the videos that we have linked, where you're dividing and then you're kind of using this 1/x thing. So this one is a lot more steps, and so I don't like to do it this way. We're starting with the same thing. And how this one works is that you're trying to factor, but you can't really factor. There's nothing you can really factor out of there. So you're artificially factoring. And so you try to factor out an x squared so that you can cancel. Now, when you do that, we're going to have an x squared just by itself on top. But when you factor out an x squared in the denominator, you end up with a fraction under the 4 because there's no x squared to actually factor out.
Mhm.
So you're like factoring is you're basically dividing it out. I can divide it out of the x squared, which leaves me with 1, but I would end up with 4/x squared. It's not there. So it's like we're forcing something to factor that doesn't normally factor.
Mhm. I like the other way better.
I do too. So we cancel out our x squareds. So I have my limit as x goes to infinity. We end up with 1/1 plus, and then the 4/x squared. I'm going to rewrite this as my 4. And then I'm going to have 1/x squared, but that is the same as 1/x squared, like
Mhm.
in parentheses squared, because that 1/x is one of those special limits that we know goes to 0 when x goes to infinity. So 1/x squared is the same as parentheses 1/x squared. And I just kind of pull that 4 in front so that I can write it in this specific way.
Mhm.
So now we can take the limit. We can't plug in infinity, but we know that the limit of 1/x is 0. So when you take the limit, you can replace that with 0. So we're going to get 1/1 plus 4 times 0 squared. And so now you're just doing some algebra. And it's basically, you're going to get 1 times 4 times 0, 1/1, and you get 1.
Yeah, but you're still breaking the rule. You're putting the 0 in the.
You
in the
can put,
denominator.
well, but see, we can put 0 in the denominator because we're not going to end up dividing by 0.
Okay, I got you. I see.
Yeah. So it's okay as long as it doesn't end up dividing by 0, and it's not in this case.
Okay.
And we didn't plug in infinity. We just knew that when we hit infinity, 1/x becomes 0.
Okay.
So we can replace that with 0. So I like the top method better than this method.
Yeah, it's an awful lot of way to go to get the same answer.
Yep. Mm-hmm. Yeah, I don't know why they teach the bottom method, honestly. Maybe because the bottom method is easier to explain in text, like when you're trying to show your work in like written down, versus the top I had to kind of explain verbally.
Mm-hmm.
So we'll do another one like this. And this one's going to negative infinity, but it's going to be the same kind of thing. So we've got the limit as x goes to negative infinity here of x cubed plus 2x plus 1 over 4x cubed minus 2x squared plus 9. So just kind of thinking about end behavior, again, this is going to go to a horizontal asymptote. So you just have to know, okay, when we do our horizontal asymptote, we're only caring about those first terms. And so when we plug in really big numbers, adding 1 and adding 9 doesn't matter because you've got a giant thing plus 1, still giant.
Mhm.
When you've got something that's cubed, adding something that's 2 times that number is so small compared to something cubed that we can also ignore that. And the
Okay.
same thing with the negative 2x squared is when you compare it to something x cubed, it's just so small in comparison. So we only really need to look at those first terms, the leading coefficients, x cubed over 4x cubed. So you can cancel out your x cubes, which gives you 1 over 4. And we haven't actually taken the limit. We're just canceling stuff out. And then, well, my answer is going to be 1 over 4 because there's nothing to plug into. It's just 1 over 4.
Mhm.
And that's the horizontal asymptote. Now, doing this the other way is going to involve a lot more algebra. And hopefully I have enough room here to show every step.
Mhm.
So in this case, we're going to factor out x cubed. So you always start with that highest term that you want to factor out. So when I have something like this that I'm really factoring out, I'm going to actually write my factoring step just so I don't mess it up. So I am dividing each term by x cubed. And then in the denominator, I'm also going to factor out an x cubed. And I can already see I'm certainly not going to have enough room here. So I got to add an extra slide. So when you factor that out, our x cubes that we factored out cancel. And then I need to simplify inside each of these fractions here. So I'm just gonna, I definitely need more room here. So I've got the limit as x goes to negative infinity. And luckily I wrote this one on a piece of paper because I knew that I was not going to remember. So on the top, we get 1 plus 2 over x squared plus 1 over x cubed. And then the bottom, we get 4 minus 2 over x plus 9 over x cubed. Basically, when you factor out those x cubed parts, and then you simplify each of those fractions that we created. So anything that's all these x squareds, x cubed, I'm going to rewrite these. So that way they're all a 1 over x. So I get 1 plus, and I'm going to put the constant in front. So the 1 over x squared is 1 over x quantity squared. And then 1 over x cubed is 1 over x quantity cubed. And I've got 4 minus 2 times 1 over x. And then plus 9 times 1 over x quantity cubed. Now, everything that is 1 over x, that is going to become 0 when I take the limit, because the limit as x goes to negative infinity of 1 over x is 0.
Okay.
So I'm going to take the limit, which means now that limit notation disappears and I can replace them with 0. So I had 1 plus 2 times 0 squared plus 0 cubed over 4 minus 2 times 0 plus 9 times 0 cubed. And you end up with 1 over 4 with a lot more steps. So for number 5 on the homework, I recommend doing the top versus the bottom for that one. That is my recommendation.
I mean,
And
I understand the math theory of the second version, right? It made sense. So you just zeroed everything out at the end of the day, and then you wound up with the same answer.
Yes.
And
So in theory, if you follow your steps, you're just eliminating all those steps and going right to that first.
Right. Yeah.
You know.
I feel like the top is more understanding the concept, while the bottom is more of understanding the skills.
Yeah. Yeah.
So you get there in both directions. It's like, do you want to just, which one, if you understand the concept, you can kind of think through it with this whole giant +1 is still giant kind of thing, or you can just say, I'm just sticking with what I know with my algebra, and you can work through all the algebra and get the same answer.
And use extra paper.
Yeah. Now, when you get to calculus, you'll learn something called L'Hopital's rule, where you take the derivative of the top and then the derivative of the bottom, and then that usually, and this is something you can't use at infinity because you still would have to somehow figure out what to do with infinity, but it works for if you're looking at a specific number and none of those other techniques worked, and then it creates a new function that you can then plug in and get the right answer. It's really bizarre that it works. We'll say that. I don't quite understand the theory of that one, but I know it works. And so it's like my favorite rule when I'm trying to find limits because it works every time pretty much. Okay. But I think that's like 2 or 3 weeks into Calc 1 that you learn that.
Okay.
But
are they going to let you teach Calc 1 yet?
When I looked today, because I still haven't been told what classes I'm teaching, and I'm like, I have to set these up tomorrow. They still have not updated it, so I don't know.
Okay.
So tomorrow, I'm assuming they'll finally update it and then assign the class. And if they don't, if they're a little behind, then it might be Wednesday that I might find out. So I don't know.
You had mentioned that they kind of like you in pre-calc, so.
They do. It would be nice to get calculus, but knowing that they haven't given me a calculus class in 2 years, so it's probably not going to happen, but I can hope. I can hope.
I'll pray for you.
If you get stuck in calculus and I'm not your teacher, you're still welcome to reach out to me because I love calculus. So
I appreciate that.
So,
right.
Yep. So that's all you need for number 5.
Well, I appreciate that, and yeah, because that was. I got to that one. I was like, "What the hell do I do with this?"
Yeah, I mean, you could graph it, but still, if you don't really understand what it's asking for.
I used Desmos to graph it, and when you graph it, you wind up with 3 lines. You wind up with 3 curves.
It must have. Oh, what is it? I don't know. I'm actually going to pull up Desmos because I don't remember what it looked like. I didn't do it that way.
Yeah, let me pull up. I don't have
Yeah, I'm pulling up the assignment too, so I can see what the exact equation is. Oh yes, this one is going to have 3 parts. That's right. Oh, Well, I just learned that you can copy the equation from Word into Desmos and it will graph it.
No, really? Yeah,
Yep, I
do
just
something?
did that. I just copied it just from the Word document and pasted it, and it did it right.
Okay, this is good because I put the answer as D and E on this one. Like, no, it's not
So
like-
when you look at it graphically, you got to zoom out enough. And okay, this is almost zoomed out too much. I can't actually see what's going on here. What you're looking at is the outside parts. You don't care that the inside has this other third thing going on.
Right.
You only care about the outside. So you can like click here. It's at 2.001. And it's like
it's
basically
hanging on too.
it's
right?
hanging out in 2. So if you
Yeah.
do it graphically, your limit is 2. That is the horizontal asymptote. You have to like zoom out enough that you kind of see that, because otherwise
This is where it confused me because it's got a horizontal asymptote, but it's also, it looks like it's got a vertical one too.
it does. Yeah. But we don't care about the vertical because we're looking at infinity. So,
So you only care about the horizontal when you're dealing with infinity?
yep.
Oh, see, there's
Yep.
another one of the little rules.
Yeah. So
Okay.
if we were caring about the vertical, that would be if it wanted X goes to like 3 or -3, where the vertical asymptotes occur.
Mm-hmm.
So if it asked you, okay, what happens when X goes to 3, that would be DNE because the left and the right side don't match at that point.
Mm-hmm.
But that's not what it's asking for. It's asking for infinity, so we don't care.
Got it.
Yep.
All right. All right. Well, now I can finish this up and get it over to you.
Yep. And this one is an easy one for me to grade. It goes pretty quickly because there's not a lot of work to show. It's just
No, there
You know?
wasn't. It was.
but that also means because I have to split up 100 points within 5 questions with no work, that it's like if you get it wrong, you just kind
You
of
lose
lose.
it.
You lose a lot because 100
It's what it
divided by,
is. It's what it is. So.
Yeah, exactly. So
Well, it's been a pleasure, and I'm hoping we'll cross paths again. We might. We'll see how
Yeah.
I'm getting a final grade in this class. We're kind of right on the theater. So, and to be honest with you, it's this was a lot of material for 8 weeks. A lot of
yes.